All right, today we are going to start by talking about sinusoidal signals. So I'm going to attempt to draw something here. It's just supposed to be a simple sinusoidal signal, but unfortunately I cannot draw them particularly well, so please bear with me. So this is going to be our vertical axis. And let's say that our signal of interest is a voltage for what it's worth. So let's call it V of t, like so. And then here is our horizontal axis, and this will be our time axis, like so. And let's draw the signal in blue. Um, so we might have something like this. Anyway, so this signal right here, imagine if it were drawn smoothly. V of t could be expressed as either a sine function or a cosine function, right? So we could call this V of t, let's call it Vm cosine omega t plus some phase angle theta. And we could just as easily call this Vm sine omega t plus some phase angle phi. And so what I want us to do really quickly is talk about the different parts of a sinusoidal function and all of that kind of good stuff. And then we're going to talk about how we manipulate sinusoids, and then finally how all of this connects to circuit analysis. Okay. So let's start with our amplitude. So the distance between the horizontal axis and the peak value of our sinusoid is what's known as our amplitude, and we designate that with the symbol Vm. So that's just telling us the size of our sinusoidal signal. So if Vm were 1, then that means that our sinusoid would be oscillating between +1 and -1. If Vm were 15, then our sinusoid would be oscillating between +15 and -15. Okay, so Jake can't hear me, but Sam can, so it sounds like people can hear me. Okay. Okay, so let me write some things down here. So Vm is the amplitude, and you may also hear me call this the magnitude of the sinusoidal signal. And it represents the signal's strength. So the higher that value is, the stronger the signal is. So 15 volts is a stronger signal than 1 volt. Now I want to talk about the angular frequency omega. So omega is the angular frequency of the sinusoid. Always measured in radians per second. And it defines or represents the speed of the sinusoidal oscillations. So when omega is very, very large, our signal oscillates between its positive and negative maximum faster than a signal whose omega is very, very small. Now, if we were to look at a sinusoidal signal as a function of time, like I have tried to draw here, we can't look at this and infer what omega is directly, but there is a way that we can determine it from looking at the graph. So I want to talk about that really quickly here. So these are all going to be kind of subparts underneath our explanation of what omega is. Okay, so I'm going to define the distance between successive positive peaks here as our period t. So our period t is the total amount of time it takes to complete a single cycle or a single oscillation of our waveform. So the inverse of t, which we're going to call f, is the linear frequency and it represents the number of cycles that are completed in 1 second. So linear frequency is measured in hertz, where a hertz is simply 1 over a second. Okay. So let's talk about period and frequency here. Okay, so period is the total amount of time it takes for one cycle to complete, and frequency is the total number of cycles that are completed in 1 second. So period is time per cycle, and frequency is cycle per time. So these two quantities, T and F, are inversely related to each other. And I believe this is something that you guys learned way back in Engineering 120. Okay. So F is simply the inverse of T, and by extension, T is just the inverse of F. So if we can determine the period or the periodicity of a sinusoidal waveform, then we take the inverse of that period or that amount of time, and that gives us our linear frequency F. Well, our angular frequency omega is simply the total angle that is completed. So omega is nothing more than 2 pi radians times our linear frequency, which gives us units of radians per second. And from this, we could also say that omega is simply then 2 pi over our period. So now we know that if we can determine the period of our sinusoidal signal, we can do a very easy calculation in order to determine its angular frequency, omega. Okay. So we figured out, or I've explained what VM is. I've explained what omega is. And so now let's talk about what's called our phase angles here. Okay. So I've given our phase angle for our cosine function a symbol of theta, and I've given the phase angle for our sine function a symbol of phi. The reason why I have done this is because I just want to make sure that you guys understand that these are two different angles, and it's going to depend on whether we're looking at this signal as a cosine function or a sine function as to what that phase angle is. Okay, so I'm going to express everything in terms of theta as a phase angle, and everything that I'm going to mention is applicable to phi as a phase angle as well. Okay. So theta is the phase angle of the sinusoidal signal, and it represents how far in time the signal has been advanced or delayed. So scrolling back up here and looking at my poorly drawn sinusoidal function, okay? So let's say, let me do this in, I don't know, purple so I can erase it here in a moment. Let's say that I had a signal, let's just call it x of t is equal to cosine of omega t plus 0 degrees. So effectively, let's say that our phase angle was 0. At what time would we expect our signal to be at its maximum?
One. No, 0. I'm sorry.
0. Okay. So at cosine of 0 is 1, which is the maximum value of a cosine function, right? And then cosine of 180 degrees would be -1. Cosine of plus or minus 90 degrees is 0. All stuff that we've hopefully seen before in our prior math classes and all of that kind of good stuff. So anyway, with a phase angle of 0 degrees, we expect our cosine function to hit its maximum value at t is equal to 0, right? Well, we can see by looking at this graph, let me do this in green, that there is a certain amount of delay here. I'm going to call it delta t between t is equal to 0 and when our cosine function hits its maximum value. Okay, I'm going to call this delta t1 for the sake of argument, right? So if we view this signal that I've drawn in blue as a cosine function, it is delayed by some small amount because it hits its peak value after t is equal to 0. Now, instead, actually, let me talk about it this way. So let's say we have y of t is equal to sine omega t plus 0 degrees. So at what time should we expect that sine function to equal 0?
t/2.
So for a sine function at the period over 2, we would actually expect it to have a value of its maximum. So 1, in this case, since the amplitude is understood to be 1. So I believe, and you can check with your calculators if you want to, that sine of 0 is equal to 0. And then sine of 90 degrees is equal to 1. Sine of 180 degrees is equal to 0. Sine of negative 90 degrees, positive 270 degrees is equal to -1, and so on and so forth. So what I'm trying to explain here, and sounds like I'm doing it poorly, but we'll all get it in the end, is that if we treated this signal in blue as a sine function, or I'm going to call this delta t2, our signal would actually be advanced by some small amount. And the reason that I'm saying that it is advanced is because it hits 0 at a time earlier than t is equal to 0, whereas our cosine function was delayed because it hits its maximum value at a time later than t is equal to 0. And this amount of advancement or delay is directly related to the phase angle of the sinusoid. Okay. So if the sinusoid is advanced, which simply means shifted to the left, then its phase angle is positive, and given by theta is equal to omega times delta t. if the sinusoid is delayed, or shifted to the right, then its phase angle is negative. And given by theta is equal to negative omega times delta t. So knowing the phase angle lets us determine how far it has been advanced or delayed, and then knowing how far the signal has been advanced or delayed lets us work backwards to find our phase angle. Okay. So before we move along from the basics here, does anybody have any questions about what amplitude or magnitude means, what either linear frequency, angular frequency, or period means, or what phase angles mean? Okay, so now let's talk about manipulating sinusoids. So realistically, there are only three rules that we need to pay attention to whenever we are trying to manipulate a sinusoid, okay? So our first rule is that all signals must be expressed exclusively as sine or cosine functions. So this means that we need to effectively pick a reference. Well, in electrical engineering, for reasons that I will explain later in this class meeting, we use cosine as our reference for everything, okay? So if we ever have a function or a signal that is expressed as a sine function, we convert it into a cosine function. Does anybody know how to convert a sine function into a cosine function?
You just subtract half the period.
So we're going to subtract 90 degrees, okay, which is effectively the same thing, okay? So trig identities that we're going to have to use, and I'm going to say several, but probably not as many as I would normally do for brevity's sake. And I'll let you know which ones I actually expect you to remember. And that list is very, very short, okay? So if we have sine of omega t plus some phase angle phi, this is the same thing as cosine of omega t plus phi minus 90 degrees, meaning we simply subtract 90 degrees from whatever phase angle our sine function has to give us the phase angle of our cosine function. So these two things kind of put together would be theta. Okay. Now, we won't necessarily or I say necessarily, we won't ever have to do this, but for the sake of argument, we could also go the opposite way, right? So if we had cosine omega t plus theta, that's simply going to be sine omega t plus theta plus 90 degrees, where theta plus 90 is phi, our phase angle for our sine function, right? So to summarize this very briefly, to go from sine to cosine, we subtract 90 degrees. To go from cosine to sine, we simply add 90 degrees. Okay. Nothing particularly difficult about that. We'll use that here shortly. Our second rule is that all signals must be expressed exclusively with positive amplitudes. So the trig identities that are associated with this are as follows. So if we have negative sine of omega t plus phi, that is the same as positive sine omega t plus phi plus or minus 180 degrees. And the reason why we can do plus 180 degrees or minus 180 degrees, and both of them are equally valid, is because that brings us exactly halfway around a unit circle, or shifts things by exactly half of a period. Very similarly, we could say that negative cosine omega t plus theta is going to be equal to positive cosine omega t plus theta plus or minus 180 degrees. So regardless of if we have a negative sine function or a negative cosine function, we can convert it into a positive function by simply adding or subtracting 180 degrees. Our third rule is that all signals must have the same frequency. So I did not specify whether I was talking about angular frequency or linear frequency here, because those two are just related to each other by a constant factor of 2 pi. So as long as all of the angular frequencies are the same or all of the linear frequencies are the same, we are good to go to manipulate sinusoids. If they are not the same, there are no trig identities or anything like that to fix that. We just can't really do anything with it, at least for the purposes of engineering 221. When we have different angular frequencies, we'll cover that in much greater detail in circuits 2 for those of you who are picking up an electrical engineering degree or a minor in electrical engineering. All right, so let's look at in-class assignment problem number 1. So in this particular problem, we are asked to express each of the following sinusoidal functions as a single cosine function. So parts A and B are going to be fairly straightforward. part C is going to require a little bit of work on our part, but I'm going to show you a much easier way to do things for that one. Okay. So this is me skipping, I think, literally 8 trig identities that I would have normally taught, and I'm just going to jump straight ahead to the easy way for you guys. All right, so let's look at part A here. So we have f of t is 300 sine 628t, and we want to convert that to a cosine function. So what do we do? So if we look back at our trig identities here, to go from sine to cosine, we simply subtract 90 degrees from the phase angle. So our phase angle here was implied to be 0. So this is literally just going to be 300 cosine 628t minus 90 degrees. For part B, we have g of t is equal to -4 sine of 3 pi t plus 30 degrees. So the first thing that I'm going to do is I'm going to get rid of the negative sign out front by adding 180 degrees. So that's going to look like 4 sine 3 pi t plus 210 degrees. And now I'm going to subtract 90 degrees from that phase angle in order to convert from sine to cosine. So that would look like 4 cosine 3 pi t. So 210 minus 90 degrees is positive 120. And there we go. So for part C, I'm going to pull a window over, and we're going to play around with Desmos graphing here really quickly. Hopefully you guys can all see this. So the first thing that I'm going to put in here is that 14 sine 50t minus 5 degrees. So let me call this x1. No, I don't want to do x1. y1 of x, just so I don't have to declare a new variable and all of that kind of stuff in Desmos, because it's annoying and I don't remember exactly how to do it, is equal to 14 times, I think it was sine 50x minus 5. Now, this is looking like a wall of red right now, just because I have my settings odd. So instead of making my x-axis from -10 to +10, let's see what happens if we make it from -0.5 to +0.5. And let's make our y-axis go from -20 to +20. So things look a little bit more settled down here, but we do have a small issue. So 50, our angular frequency, measured in radians per second, times our time, x, measured in seconds, gives us an angle that is expressed in radians. But our phase angle 5 was expressed in degrees. So what I'm going to do is I'm just going to multiply that 5 by pi over 180, so that all of the angles inside of my sine function are expressed in radians. Okay, So that's the first part of the two things that we're asked to add together. Now I'm going to do the second part. So let me look at this real quick. So that was 10 cosine 50t. So 10 times cosine 50x, and 0 is 0 regardless of whether we're looking at radians or degrees. Sorry. And now what I'm going to do, I believe, so it's 14 minus 10, okay? So I'm just going to call this y3 of x is just y1 of x minus y2 of x. And now I'm going to turn these off. So it looks to me like the combination of those two sinusoidal signals can be expressed as a single sinusoid. Okay. Just based on this graph, it looks like we're oscillating between something very close to plus and minus 18. I just mouse over one of these dots. I bet I can figure it out. 17.9, probably, and some rounding error. Okay. Now, there is a way to do this math with a ridiculous amount of trig. And when I say a ridiculous amount of trig, I mean we're going to apply several different trig identities to convert everything down, do a bunch of algebraic manipulation, and then apply a few different trig identities to put things back in terms of a single sinusoidal function. If you want to see me suffer through that math, you are more than welcome to watch one of my older YouTube videos, okay? But because I'm trying to save us some time, I'm going to talk about a way to do this that is much, much more straightforward, okay? So let's write some things down here, okay? So we have h of t is equal to 14 sine 50t minus 5 degrees minus 10 cosine 50t. So the first thing that I'm going to do is I'm going to convert that sine function thing into a cosine function. So that's going to look like 14 cosine 50t minus 95 degrees minus 10 cosine 50t, like so. I put everything in terms of cosine functions because I said earlier, electrical engineers use cosine as a reference. Now what I'm going to do, and it's going to seem like magic for right now, but I will explain exactly what's going on here in a little bit, is we are going to represent these two functions, these two sinusoidal functions, as polar form complex numbers, okay? So we know that a polar form complex number is characterized by a magnitude and a phase angle. So what is the magnitude of this guy right here?
$14.
14. What is the phase angle?
Negative 95 degrees.
Negative 95 degrees. All right. Now let's do this guy over here. What's the magnitude of 10 cosine 50t?
10.
And what's our phase angle, please?
0.
All right. So if you could, please put that in your calculator and tell me what you get.
I got 17.9 less than negative 128.8167.
So that less than sign is very much not a less than sign. That is the angle operator sign on your calculator. But you got 17.8998. So that's 17.90 effectively, with an angle of negative 128.817 degrees. Somebody tell me what they got in rectangular form.
Got a negative 11.22 minus 13.95 I.
Oops, you said 13.95.
95, yes, sir.
I transposed it. 947 is what I got when I did it. Okay, so I'm gonna bring Desmos back up and I want to show you guys something here really quickly. So let's make a new thing here. Let's call it Y4. So we got 17.9 cosine 50x minus 128.817. And then I'm going to multiply that by pi over 180. And I will be damned if that purple curve doesn't completely overlap the green curve. What do you think it means that the purple curve completely overlaps the green curve?
They're the same thing.
Yes, that is exactly right. So what we just did was use simple, complex subtraction in this case in order to avoid literally 30 minutes worth of trig identity manipulation. So that's pretty damn amazing. Okay, but we can actually do something pretty interesting as well with our rectangular form. Okay, so let me pull Desmos back up here. So let me do Y5. So we had negative 11.220. I'm going to multiply this by cosine 50x with no phase angle whatsoever. And now I'm going to add 13.947 times sine of 50x with no phase angle. And once again, things have completely overlapped. So both the polar form and the rectangular form of our complex number can give us what we're looking for. I just want to point out this last thing using the rectangular form, because in a couple of your different homework problems, and I might work one of those here in just a second, just to make sure that we're understanding what's going on. I can take my rectangular form of my resultant complex number and simply flip the sign on the imaginary part in order to express my answer as a sum of sinusoids where my phase angles are 0. I don't particularly know why that's important. I just know that you are asked to do it on multiple occasions in your homework set. So I'm trying to give you a cheap and easy way to figure that out. So let's look at a homework problem really quickly. So this should be homework set number 19. Leading and lagging, we haven't talked about that yet. That's what we're going to do here in a moment. So this guy right here, right? This particular homework problem, we're told that we have a signal that is just the combination of these two sinusoids, and we want to express it in terms of a cosine function with no phase angle plus a sine function with no phase angle, or a single cosine function with some phase angle phi. Okay, so in order to work this problem, all I'm going to do is I'm going to take 43 angle negative 111, which is just my magnitude and my phase angle, minus 37 angle. So 126 minus 90 degrees would be positive 36 degrees. And I get negative 45.343 and some change minus 61.892 and some change is the imaginary part. So I'm going to change the sign. So it's positive 61.892. I'm going to convert that result into polar form, and I get 76.724 with a phase angle of negative 126.227. And I'm going to submit my answers, and I'll be damned if I didn't get that entire problem right using exactly 0 of the trig identities it was expecting me to, because complex numbers are amazing. So for this particular homework set, use complex numbers as often as you can in order to make it less horrifying. So anyway, I'm going to take this result right here, and I'm going to convert it back by simply keeping the magnitude. I'm just going to put cosine 50t because that part can't change. And now I'm going to take my phase angle. And I'll be damned if that is not exactly what we were trying to find. Okay. So before I go to the next part of the lecture, does anybody have any questions? All right. So let's now talk about leading and lagging. So that I have a voltage signal, so let's just call it V of t is equal to 8 cosine 10t minus 45 degrees volts. And a current signal, and let's just call this 2 cosine 10t plus 30 degrees amps. if I were to plot these signals, actually, I might use Desmos for this because I've established, I think, very well that I can't draw sinusoids to save my damn life. Let me clear all this junk out. So let's say that we have V is equal to, I think I said 8 cosine 10 t minus 45 degrees. So multiply that by pi over 180. I need to convert that t to an x so it knows what the hell I'm talking about. And I was 2 cosine 10 plus 30. All right, so I have these two sinusoidal signals on the screen. I hope you guys can all see them, right? So leading and lagging is simply us figuring out which current, or excuse me, which signal hits its peak value either earlier or later in time, okay? So for example, I can see that the peak value of my current waveform is occurring here in the ballpark of negative 0.0533 seconds. So roughly at t is equal to negative 53.3 milliseconds. And I can see that my voltage signal is hitting its peak value at 78.5 milliseconds. So I would say, based on this picture, that the current is leading the voltage because it hits its peak value earlier in time. Or I could say that the voltage is lagging the current because it hits its peak value later in time. Okay. That's all leading and lagging particularly means. Okay. So a signal leads another signal if it hits its maximum value earlier in time, and a signal lags another signal if it hits its maximum value later in time. Now, I personally find leading and lagging a difficult concept when I'm looking at time domain signals like the ones that are expressed in this graph. Okay. For whatever reason, to me, it seems counterintuitive that the voltage here is lagging the current, and by extension, the current is leading the voltage. So my preferred way to look at leading and lagging signals is by using what's called a phase diagram. Okay. So a phase diagram is nothing more than a snapshot of our signals at a particular instant in time. And I choose the instant t is equal to 0 so that the whole omega t bit effectively just goes away, right? So I could make a phase diagram for these two signals like this. So the positive horizontal axis is for 0 degrees. Up here is 90. Over here is plus or minus 180. And then down here is negative 90 degrees. So my voltage waveform, which I'm going to do in red, has a length of 8 and an angle of negative 45 degrees. So it would be something like this. And my current, I'm going to do in blue, would have a length of positive 2 and an angle of positive 30 degrees. So something akin to this. So if I want to find out by how much does I of t lead V of t, what I do is I start measuring from V of t, and I keep going until I hit I of t, like so. So this would be 45 degrees to get from here to the horizontal axis, and then another 30 degrees to get from the horizontal axis up to the projection of I of t. So I simply add those together to get 75 degrees. So anytime I'm measuring counterclockwise, I'm measuring leading, because I'm saying how much more is that signal advanced than the one I'm measuring it against. If I wanted to know by how much does I of t lag V of t, I would do the same thing, except that I would measure clockwise, right? So this bit right here is 45 degrees, then I have another 90, then I have a 90, then I have a 60, so that's 180 plus 60 is 240 plus 45 is 285. That looks way like 288, sorry. 285 degrees. Okay. So those are the basics of leading and lagging. I understand that I went over it rather quickly, and so I'm going to take a moment to work on one of you guys' homework problems so that you can see it a little bit more in practice. So let me pull up that web work assignment again. Let's look back at problem 1. So in this first problem, we are asked by how much, or find the angle by which our current lags our voltage if our voltage is 91 cosine 120 pi t minus 30 degrees. Okay, so let's just work one part of this thing. Let's do C for what it's worth, okay? So in part C, let me pull this over here so I can see it. We know that our voltage is 91 cosine 120 pi t minus 30 degrees. And the current that we're given is negative 6.3 cosine 120 pi t minus 96 degrees. So because I'm manipulating sinusoids here, I need to make sure that I express that current with a positive amplitude. So that's going to look like positive 6.3 cosine 120 pi t. And I'm just going to add 180 degrees. So I believe that's going to look like plus 86, but let me throw that in my calculator to make sure. Negative 96 plus 180, 84. So I'm going to draw my phase diagram. Zero, 90, plus or minus 180, negative 90. Let's put the voltage in red again. So the only thing that really matters here is the angle. So negative 30 degrees would be somewhere around my current. It has an angle of positive 84 degrees. So that would be something like this. And we are asked find the angle by which I lags V. So our voltage waveform is our reference. Okay, so we're going to start measuring from our voltage waveform. And because we were specifically asked to find the angle by which I lags V, we're going to go clockwise around our circle. So that's going to look like 60 degrees, 90 degrees, another 90 degrees, and then up here is 6 degrees, right? So 180 plus 60 is 240, plus 6 more is 246 degrees. If I put 246 degrees in here and submit my answers, it tells me that I am wrong. Okay. Now, I am not so arrogant to say that it's impossible that I have made a mistake here, but I truly don't think that I have. What I believe the problem is that web work, as I'm sure you all have experienced, is kind of dumb at times. And web work does not understand that positive 246 degrees is the exact same thing as 246 minus 360 is negative 114 degrees. And I'll be damned if it doesn't think my answer is now correct. Okay, so there is, I don't want to say it's an issue, but the problem with this particular homework problem, and any one by which you're determining leading and lagging, is that web work doesn't understand that there are equivalent angles. So if you believe that you have done the process correctly, and it's telling you that you do not have the correct answer, simply try adding or subtracting 360 degrees, which is literally the exact same angle. And I guarantee you that one of those three things, so either your original answer, your answer plus 360 degrees, or your answer minus 360 degrees, web work is going to tell you that one of those three is correct. Okay. Any questions on leading and lagging? All right. So I'm going to go out on a limb here and say that we have a good understanding of sinusoidal signals. I'm saying that only because you guys aren't asking any questions of me, so I don't have anything else to really talk about until you do with regards to that. So now let's bring circuit analysis back to the fold, okay? So let's say that I have the following circuit. Actually, so let me call this an introduction to steady state sinusoidal circuit analysis. So let's say that I have the following circuit where I have just a 2 amp source. Here is a 5 ohm resistor. And here is a 0.5 Henry inductance. And what I want to figure out is the voltage drop across that source. Could anybody analyze this circuit quickly and tell me what that voltage Vs should be equal to?
At a steady state, 10 volts.
Exactly right. So this is a DC circuit. There's nothing to tell us that we have any transient analysis to worry about because there are no switches or anything. So there's no opportunities for our circuit to change. So just using Ohm's law, we could say that Vs is equal to 2 amps times 5 ohms is equal to 10 volts. So if I have a DC excitation, I get a DC response. Now, let's take this same circuit, but we're going to sinusoidally excite it. And our ultimate goal is once again just to figure out what the voltage drop across our source is as a function of time. So let's say that IS of t is 2 cosine 5t amps. Actually, I'm going to explicitly say 5t plus 0 degrees here, amps. So if we sinusoidally excite our system, it stands to reason that our response will also be a sinusoidal signal. So I say that it will be of the form Vm cosine 5t plus some phase angle theta volts. So if I put a DC source in, I get a DC signal out. If I put a sinusoidal signal in, I should get a sinusoidal signal out. Hopefully that's not too much of a stretch of the imagination for you guys to understand. So, assuming that you're willing to take me at my word that our response should look in this form, how do you think we might go about solving for that?
Would we not just multiply the first equation by the resistor value?
So if we multiply the first equation by the resistor value, what that's going to give us is the voltage drop across our resistor. So let me label that really quickly, right? So here is VR of T, and you have suggested that VR of T is 5 ohms times 2 cosine 5t plus 0 degrees amps, which comes out to be simply 10 cosine 5t plus 0 degrees volts, right? So we can't say that that's our source voltage, because since our current is changing, we know that our inductor should have some voltage drop across it, right? Because we know that the voltage drop across an inductor is given by the inductance value times the derivative of the current that's flowing through it. So let's play around with this a little bit. So we have 0.5 henries, where a henry is a volt second per amp. We could pull that 2 out of our derivative because that's just a constant. So that's going to look like 2 amps. How do I take the derivative of cosine 5t plus 10 degrees?
Is it supposed to be 10 degrees or 0 degrees?
Oh, it is supposed to be 0 degrees. Thank you for that. How do I take the derivative of 2 cosine 5t plus 0 degrees?
It's going to be a chain rule. So you're going to take the derivative of the inside multiplied by the actual derivative of the function.
Okay, so what's the derivative of 5t with respect to t?
That's just going to be 5.
5. All right, so that's 5. That is our angular frequency, so that means it has units of radians per second. Well, radians is a dimensionless quantity, so I'm just going to call this 5 per second. What's the derivative of cosine of, let's say, x?
Negative sign.
Negative sine 5t. So let's look at what happens with all these units here. So this amp cancels this amp, this second cancels this per second, so we're left with a voltage. Half times 2 is 1, times 5 is 5. So that's going to give us negative 5 sine 5t volts. And applying Kirchhoff's voltage law, we could say that Vs of t is nothing more than Vr of t plus VL of t, which would be 10 cosine 5t minus 5 sine 5t volts. But this part right here doesn't look like this part right here. But I think we know how to fix that. So somebody tell me what to do. And it's literally just
Convert the sine to cosine, and then just addition, subtraction.
Yep, so 10 cosine 5t minus 5 cosine 5t minus 90 degrees volts. Okay, absolutely there. Then what we did earlier is once we got to this point, we effectively just converted it into polar form complex numbers, right? So that would be 10 angle 0 degrees minus 5 angle negative 90 degrees. Putting that in my calculator, I get 10 angle 0 minus 5 angle negative 90. $11.180 with an angle of 26.565 volts, and then converting this back into the sinusoidal function, I get Vs of t is 11.180 cosine 5t plus 26.565 degrees volts. So that process wasn't particularly difficult, because we already knew that we could use complex numbers to avoid a bunch of gross trig and all of that kind of good stuff. But there is a way to make even this relatively okay amount of math much, much easier and much more simple. Okay. And so that's what we're going to talk about now. So I want to explain to you guys a little bit about why this works. Okay. So let's say, let me go to a new page here, that I have a linear black box network. On the left-hand side, I'm going to have my excitation source, which I'm just going to call x1 of t. And on the right-hand side, I'm going to have my output signal, which for this case, we're going to call it a voltage, y1 of t. And what we just found is that when x1 of t is of the form x sub m cosine omega t plus some phase angle theta x, then y can be expressed of the form y sub m cosine omega t plus theta y. Okay. That's literally what we just did with that last example problem. Now, if I take my black box network and I excite it with a different signal, so let's say that here I have some signal x2 of t. My response should be some signal y2 of t. So I'm going to go out on a limb here, and I'm going to ask you guys a question about this. So let's say that x2 was xm sine omega t plus some phase angle theta x. What would you expect y2 of t to look like? So another way to phrase this question is, if I put a cosine function in and I get a cosine function out, what do you think is going to happen if I put a sine function as my input?
Get a sine function out.
I get a sine function as my output. Exactly right. Do you guys recall the homogeneity or scaling property of linearity? It's okay if you don't. I think that was the lecture that I had to miss due to jury duty. So I'm not 100% convinced that all of you actually watched the damn thing anyway. But if anybody happens to remember it, let me know what you think it is.
Does that mean that just anytime we apply a scalar to our source, that it also applies to our output?
That is exactly right. So if we scale our input by some amount, then we scale our output by the exact same amount. So what I'm going to do is I'm going to scale our input signal by a factor of j. J is constant in time, so there is no issue with me scaling it by this factor whatsoever. So if I say that x2 is j times xm sine blah, 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 then y2 should just be j ym sine blah, blah, blah. Now, let's see what happens if I apply both of those inputs at the same time. So if I apply some signal x of t, and observe some output y of t, well, let's say that x of t is equal to xm cosine omega t plus theta x. Sorry, I don't know why that keeps popping up. Plus j xm sine omega t plus theta x. So before we sort out what's going to go on with y of t, let's think about some things here really quickly, right? So if I have a complex number, a is equal to magnitude of a angle theta a, what is the real part of a?
Is it not just the x value?
It would not be. Go to your notes from Monday. Maybe it might be slightly helpful here if I use a polar form, excuse me, an exponential form complex number, because that'll make this look nicer. So, because this is taking longer than I wanted it to, and again, this is literally in your notes from Monday, the real part should just be the magnitude times the cosine of our angle, which in this case, our angle is just omega t plus theta a. The imaginary part of this complex number a is just going to be the magnitude of a sine omega t plus theta a. So what I'm trying to drive home here is that this part right here is just the real part of some imaginary number, xm e to the j omega t plus theta x. And this part right here is just the imaginary part of that exact same complex number. So when I add that real part and that imaginary part together, what I get is just some complex signal, xm e to the j omega t plus theta x. Now, by extension, my output should just be ym cosine omega t plus theta y plus j ym sine omega t plus theta y. And I'm going to leave this in this form because I want to make it super clear here that the real part of our input corresponds to the real part of our output, and the imaginary part of our input corresponds to the imaginary part of our output. So this is why we can just choose to represent our signals as complex numbers and get exactly the correct answer by simply, doing our math in the complex domain and then spitting the answer back out in the time domain. It's all because of this superposition thought experiment here. Okay. So we've only got 20 minutes left. It's not really enough time to cover what I want to talk about next. So let's put a pin in this. Let me go back to the in-class assignment here really quickly. So we worked that first problem. We could do this second problem pretty easily. This third problem, we can't do that yet. And this fourth problem, we also can't do yet because we haven't covered that material. So I think this is a good stopping point for today just because we don't have enough time to get to it. What we are going to talk about on Wednesday's class meeting is a more formal way to analyze steady state sinusoidal circuits in what's known as the frequency domain, where everything that we've done today is what's called the time domain. All right, so does anybody have any questions for me before we knock off for the rest of today?
So for turning in the ICA before next class, do you want us to just turn in numbers 1 and 2?
So yes, let's just put it at that. Yeah, let's say yes, we are going to work problems 3 and 4. during Wednesday's class, but yeah, all I expect to see from you guys from what you're turning in today would be 1 and 2. That sounds perfectly reasonable.
Just a curiosity question, Dr. Hartman.
Sure.
Does any of this have to deal with latency?
Um, yes and no. So what I mean by that specifically is like what we're talking about right here isn't necessarily anything to do with latency. However, latency exists because it takes time for signals to propagate, and certain circuit elements, particularly inductances and capacitances, tend to cause signals to advance or delay. And that's what we're actually going to describe by a concept called impedance in our next class meeting. So loosely, yes, this has something to do with latency. Because in any real physical system, any closed path has some small amount of inductance. And any time that we have multiple conductors near each other, they exhibit some small amount of capacitance. And those two things together are what causes the delays in our signals.
Makes sense.
Yep. For what it's worth, Wednesday's class meeting will not be so esoteric, for lack of a better word. Like, I'm sure I have terrified you guys a bunch with all of this weird thought experiment stuff, but it's going to get better, I promise. Any other questions? All right. Well, I hope you guys have a great rest of your afternoon, and hopefully all of my weird talking today hasn't given you PTSD. See you guys later.
Great, Dr. Hartman. Thank you.